So Ram is the chief architect and founder of the popular DevOps tools. You may have heard of them, GC Easy, Fast Thread, Heap Hero, and yCrash, which is definitely something you should check out here. And a little bit from his bio, every single day, millions of people in North America travel, bank, and do commerce using applications that Ram has architected. There's a lot more I could talk about, but I think you get the point. So, Ram, it's all yours, and thanks for being here.
Okay, thank you, Chris. Hello, friends. How are you? So, thank you. I would like to welcome you, everyone, for attending this talk, JVM Performance Optimization and Tuning. Right? Without any more ado, let's get started. So, friends, a lot of you may be familiar with the system property, the JVM argument called as XMX. Right? This XMX, this is the maximum heap size that you can set to your Java application. Right? Say I can set my XMX to 2 GB or 4 GB or 6 GB, whatever the number. All right, you can set. So my question, I want to start off my talk with this question. Say if you're going to set your XMX to say 4 GB, will your Java application consume more than 4 GB memory? Right? The XMX is the maximum heap size. It's a JVM argument. So my question to you is, if you set this XMX as 4 GB, will your Java application consume more than this limit, what you have configured? So you're welcome to put your answers in the chat, right? So will it consume? Okay, I don't know whether anyone has seen. Okay, so the answer to this question is, it might be surprising to some of the engineers. Say this, your Java application will consume more than this XMX limit what you have configured. Right? Then people might ask, then what is the point of setting this maximum limit? Right? So to answer this question, let's see how the JVM, what are the different regions in the JVM. Right? So Java virtual machine has primarily two regions. One is the young generation and other is the old generation. So the young generation is a region where, when say someone creates an object, let's say I'm writing a code, new car, let's say that's our code I'm writing. So then that car object first is created in this young generation, right? And then if this object is going to live for a longer period, then it is promoted from this young generation to the old generation. So old generation is where all the long-lived objects are residing. So when you set XMX, you are actually only setting the size of your young generation and the old generation. But after that, there are a few more other things. Right? What are those other things are? There is another region called as metaspace. So this metaspace is the region where your application, the JVM, stores this metadata information to execute your application, like say your class definitions, method definitions. So those definitions which are required by the JVM to execute your program, they are stored in this metaspace region. Right? So this region is outside this XMX limit. So if you're going to set your XMX as 4 GB, then after that this metaspace is going to be occupied. Right? And you can set this metaspace size by this property, max metaspace size. So that's all it is? No. So after this, there is another region. Some people call this as off heap, and some people there's no actual real name given to it. So for our discussion, we'll call this as others region. So in this region, several more things are stored. Right? So your application creates a lot of threads. So if your application is running, it's running on a Tomcat server. The Tomcat executes your application through the threads, and your application may create its own internal threads. So where is the threads stored? Are the threads stored in the young generation or in the old generation or metaspace? The answer is the threads are not stored in any of these three regions. They are stored in this others region. So they occupy memory, right? And then the next one, the garbage collection is one of the integral part of the application that runs in Java virtual machine. The garbage collection is the one which evicts the unused, unreferenced objects from memory. So that needs some memory. That memory is coming from this others region. And then the third one is the code generation. See, friends, whatever the code that I write today is not the actual code that gets executed in runtime. JVM does a lot of hotspot compilations. It optimizes the code that you have written. So to do those optimizations, you need some memory. That memory is taken from this others region. Not only that. Next is socket buffers. Say, today our application, when new request comes, that creates connections. And our applications talks with several backend system of records, API gateway, database systems, external gateways. So all those connections, for all those we need connections. All those connections are coming from this others region. Similarly, file descriptors. Say if your application is reading into a file, writing into a file, we need file descriptors. That occupies memory. That comes from this others region. And when you set, when you are going to use, say, if you happen to use JNI, Java Native Interface, typically, seldom, very rarely application use JNI. So JNI is used for connecting with native C++ applications. Right? Only if your application uses that, then you will be using JNI. If you do, then that also comes from this others region. So, friends, when you set your XMX size, you are setting only the end generation, old generation size. After there is metaspace, and after there is thread stacks, garbage collection, code generation, socket buffers, and JNI. So they all occupy memory. So they are outside. Right? So one thing that what you want to do is, so people ask me, is there one global property that I can use for setting the overall size? Unfortunately, friends, there is no such one global property. So say suppose if you're going to run, if your XMX size is 4 GB, right? That means you want to run your application not on a 4 GB machine. Probably you want to take at least 6 GB machine because this metaspace and others occupies memory. And then you need to leave some room for your kernel jobs also to run, right? So typically you want to say 80-20 rule. That's what you want to be using when it comes to this kind of a sizing, right? Okay. So now we understand, okay, these are all the different regions in memory. With this knowledge, now let's go on. Let's discuss how all memory is wasted today. How all the memory is wasted today, right? So the first and the foremost reason why memory is way wasted is because of over allocation, right? See, if your developer configures XMX to be 4 GB, we assume that is the right size. No one is questioning it. Every capacity planning is done based on that assumption that 4 GB what the developer has allocated is the right size. Maybe not. So you see, here is a classic example that I want to show. So this is an very large identity management security service provider. Right? It's a cloud-based application which provides security services at real time for several major corporations in the world. So they configured their heap size to be 48 gig. Right? So it was there 48 gig right there. But when we studied this application, right, then we found it is unnecessarily over allocated. So what we did was we reduced this 48 GB XMX to 12 GB. When we dropped it, there was no degradation in the response time or CPU or anything else. Application was going through fine totally. This means the application that this provider was wasting 3/4 of its memory. Right? So and 3/4 of memory is huge in terms of EC2 computing in the cloud-based environments. So how do I come to the conclusion that whether you may have a question, how do I come to a conclusion whether I have over allocated the memory or I am optimally allocated? The answer to that can be found by analyzing your garbage collection behavior, by analyzing your garbage collection logs. That's how you will go about getting it. So we will, in the later part of the session, I will give you some pointers how you can go about analyzing your garbage collection logs. When you analyze the garbage collection logs, you will get to know whether have I over allocated or have I under allocated. I will tell you pointers and right tools to use to do it. Okay. So now let's move on. The next primary reason why memory is wasted is because of inefficient programming practices. Because of inefficient programming practices. See, a lot of time developers today waste memory predominantly because of poor programming practices. See here, let me show you. Here, this is an this is we conducted a case study on a very popular framework called Spring Boot. Spring Boot is arguably the most well-celebrated framework in the world today in the Java ecosystem. Right? So when we published white paper, we had like a pretty good readership. Like there was like 60,000 engineers who read this white paper. So I want to share it with you. See what we did was Spring Boot framework developers, they have developed an application called as Spring Boot Pet Clinic application. We took this sample application and then we conducted a stress test using Apache JMeter. A lot of you are coming from the performance testing background, so you can understand we had like 1,000 threads running concurrently, and this was a ramp up period. And then what we did was we captured a heap dump from the application when it was running. So the heap dump is basically a snapshot of memory. It shows what are all the So it shows the heap dump shows what are all the objects which are there in memory and how much space they are occupying and what objects are there, what values are there. We took that heap dump and then we analyzed it with the heap dump analysis tool. Like one tool that we use for this analysis is called as a heap hero. Right? This is the tool which we use. Right? You can take this tool and then once you upload it, the tool is going to let you know how much memory your application is wasting because of inefficient programming. See, this Spring Boot application, which is supposed to demonstrate the best practices, it was wasting 65% of its memory because of inefficient programming practices. See, here is another example that I want to show. When you upload it, so this is an heap dump of a very major travel application. So this application processes like almost 70% of North America's B2B airline ticket reservation, right? A massive deployment. This application was wasting 52%. Earlier, best practices Spring Boot was wasting 65%. This is wasting 52%. So how it's being wasted because of inefficient programming? Let's look at this example. See, here, as developers, we write data structures. We write the code. Right? So let's say now I can write a code like this. New hash map. When I do this, an hash map data structure is created in memory. So this is a Java API. But what happens is, when I write this code, Java, JVM, by default, reserves a space for 16 elements in memory. But what if the developer did not insert any element into this hash map? That's what has happened. 58% of hash map contains no elements, due to which 6.1% of memory is wasted. Right? You can see this. And it also shows okay, what are all the other things in which it is being wasted. So now the question is, why developer is not putting anything there? Right? Maybe we want to look into that. This tool also shows the source code where it is being there, and you can go ahead and fix it. Right? So now, another primary reason why memory is wasted is because of duplication of strings. Look at this, friends. This application is wasting 18.2% of memory because of duplication of strings. Look at this. We all know strings are immutable. That is, once it's created, it's going to remain like this till the end of its lifetime. You cannot modify it. It's immutable. Look at this. There is this currency code, US dollars, USD. We know string is immutable. But this application has created 47,243 instances of the string. The question is why? Why can't you reuse the same string? Why you are creating new string object every so many times? Okay? And similarly, since this is an airline ticketing application, it shows, I think these are all the airline codes or airport codes. Right? If this is a very large string which has like a 2,339 characters. So there is like a 354 such instances of large strings exist in memory, due to which 1.59 megabytes of memory is wasted. If I want to see where those objects are being created and wasted, I just need to click here. So now I'm clicking here. You see this shows the code path, and it shows, okay, this is all the duplicate data structure. So now seeing this, you can go ahead and fix this code path. So you can optimize this memory, right? So friends, now some of you may have a question, do I need to really care about memory? Because memory is very cheap. Why do I need to care about it? See, this argument, look at this. In 1970s, 1 byte of memory was $1. Let me repeat. In 1970s, 1 byte of memory was $1. So roughly, if I'm going to take one photograph in my cell phone today, it is 1 MB. That means the cost to load this new photograph into memory back in 1970s system would have been $1 million US. Just one photograph to load it into memory would have been $1 million US. So taking into inflation into account, maybe it may be what $10 million, right? But given that the cost of memory has come down to fraction, now it is almost negligible. I can't even measure what is 1 byte of memory is going to be. It's almost negligible, right? But still, I would argue memory is not cheap. Here is my rationale to it. Friend, as engineers, at the level we work, there is only 4 types of compute resources are available. One is CPU, second is memory, third is storage, and fourth is network. So these are the 4 compute resources. See, just take one AWS EC2 instance or Google Cloud instance or Azure instance, take any instance. In that one instance, which resource gets saturated first? Out of these 4 resources, saying just in one AWS EC2 instance, which resource gets saturated first? Is it CPU? Is it memory? Is it storage? Or is it network? Friends, for most of the applications, most of the applications, it is the memory which gets saturated first. CPU is always at 50-60%. There is abundant storage, there is abundant network. So always memory gets saturated first, CPU before CPU saturates. So if you see, other 3 resources are underutilized or partially utilized. Just because memory is getting saturated, today we end up provisioning more and more EC2 instances. So that is ballooning the computing cost on the organization. But on the other side of the spectrum, developers are wasting memory because of over allocation, because of inefficient programming practices. So if you can see this on because of inefficient programming, I can say at least most of the organization maybe average is wasting at least 50-60% of memory, which is a very big number. So if you can optimize that, then maybe you don't need to run on these many EC2 instances. Maybe if you can run on half of the EC2 instances. Think what would be the save that you can give to your organization if you're going to run on half of your EC2 instances, which is phenomenal, right? Okay, so now let's talk about garbage collection. This is another major area which influences your application's performance and as well as your cost of computing, right? So first, let's discuss what is garbage. What is garbage? Right? Okay, see, friends, we have an application, right? So when I say a new request comes to your application, let's say this is a sign-on request. When a sign-on request comes, it's going to create tons of objects. It's going to create a customer object. It's going to create it may have a username and password. And then since it creates a servlet object, it creates a database access object, it creates a connection object, and then it makes a backend call. And now database is going to give you back a result set. So each and every one I'm going to get it as a result set as object. It's going to have strings. So it's going to create tons of objects. Just to service a simple sign-on request, your application is creating several thousand objects now. So all those objects have been created in memory. Now because of created, I have serviced that request. Now the request goes away. After the request goes away, then what happens to the object that has been created in memory? They are of no use. There is no more reference to it. So only you need to evict these objects from memory. Only if you evict this object from memory, that is, you remove this object from memory, the space is going to be allowed, so that your new request can be serviced. So these objects which was created to service the old request now have become garbage. Right? So this garbage has to be removed from memory. Right? So this is garbage. So how are these garbage collected? How are these objects which is created in memory, which doesn't have any more reference, how are they removed from memory? Right? See, friends, 3-4 decades back, like 30-40 years before, and C was very pervasive during those days. Developers have to manually write the code to release the garbage from the memory. So I have to write the code. So if I create a customer object, after that thing, I have to say remove the customer object. I have to do the code manually. See, applications, business applications tends to have multiple use cases, several scenarios it does have. So developer has to be cautiously make sure he has to delete in every single use case. He deletes the object that has been created. Even if he misses or forgets to create to remove the object from one particular place, then those objects goes in memory, and then we get out of memory error. So out of memory error was happening, right, during those times. So when Java came, right, in mid 90s, Java made a big promise saying, developers, you don't worry about releasing the garbage. I will take care of removing it automatically. It is my responsibility. So you worry about only writing the business logic. You don't do this garbage collection. I will take care. That's what the JVM promised. And all developers like it because it's a less code. They can focus on the business logic, and management liked it because it's less out of layer, less impact to the customer. Boom. So since then, since the mid 90s, all languages that came, they started having this automatic garbage collection, which is wonderful. But does this automatic garbage collection have any side effects? It does have side effects. It has two primary side effects. The number one side effect is automatic garbage collection causes a very high CPU consumption. Right? See, modern applications creates tons of objects, millions of objects. Even for small sign-on request, it creates thousands of objects. So all those objects are created in memory. Now your garbage collection responsibility now to keep scanning all those millions of objects which is there in memory. You have to scan and then repeatedly scan again and again to see whether they are active. It's not just those active, you have to look at those objects references. So it is a tedious process. It has to scan completely and then it has to edit, it has to remove the unreferenced objects from memory. So it all needs every CPU consumption, every CPU compute cycles. So automatic garbage collection introduces high CPU consumption. Say today if your application CPU consumption is 60%, probably 30-40% of it is coming from the garbage collection because automatic garbage collection. And then the second another big problem that what it introduces is the long pauses. When garbage collection runs, it freezes your JVM. It pauses your JVM so that it can keep track of what is active objects, what are unreferenced objects, then it can be swept out from the memory. So it pauses your application. When it pauses, that means if any customer transactions comes in during those times, you will not get any response. See, if some customer says, "Oh, application was functioning fine normally, but suddenly I didn't get any response. But later it started to respond." It will be quite possible the garbage collection could be running at the background. Right? So you may want to do. So these are the two primary side effects what the automatic garbage collection has introduced. Right? So now, as a developer, as engineers, it is our responsibility to make sure we address these things. Right? So when you are going to tune or optimize the garbage collection performance, there is three primary metrics what you want to be studying. One of the important metric out of the three, the number one important metric is GC throughput. That is the garbage collection throughput. What does GC throughput means? Right? Say, if someone says my application GC throughput is 98%, what does it mean? Is this application is spending 98% of its time in processing the customer transactions and only 2%, the remaining 2% of time in processing the garbage collection activity. Right? Let me repeat. If someone says my garbage collection throughput is 98%, it means this application is spending 98% of its time in processing the customer activity. Only 2% of the time in processing the garbage collection activity. Right? Making sense? So now, friends, when someone says your application throughput is 98%, how does it sound to you? right? So it may sound good, it may sound great because 98% means it's an A plus grade. Our human mind has been trying to think 98% means it's a fantastic throughput. But actually, if you see, 98% throughput means your application is spending 28.8 minutes per day in garbage collection, which means 7.5 days per year in garbage collection. That means in garbage collection, when garbage collection runs, means your application is not processing any activity, customer activity, right? So it is like when garbage collection runs, you want to think your application is sleeping. Your application is actually sleeping. That's what is happening from a customer perspective. It is sleeping. That means your application is sleeping for 7.3 days per year if your throughput is 98%. Be happy if your throughput is 98%. I've seen applications have throughput like a 95%, 90%, or 85%. Sleeping is terrible, right? So 7.5 days, you need to pay for your cloud computing provider, but then you're not going to get any work from that, right? So here is a cost comparison. Because of the interest of time, I wouldn't be able to go into the detail. But let's say if you are having a throughput of 98%, and say you are working for a very massive corporations like Visa, Wells Fargo, or Google, or those kind of people, if your throughput is 98%, that means you are wasting in tune of 10 million US dollars. I took that comparison. Let's say you're going to get a AWS EC2 instance, which is a 32 gig instance. This is 10 million US dollars you're wasting. But if your throughput is 95%, that means you're wasting like a $25 million in compute, which is a huge sum. If we tune our garbage collection, we can optimize this, right? And then, see, and friend, one more thing that what you want to do, when you optimize your garbage collection, you're not just optimizing that pause time. You're in fact optimizing your overall application response time because the GC pauses your application. If I'm going to minimize my pauses, then my overall response time gets better. So here's a classic example. This is of a very large, one of the 3 largest automobile company. We help them in the tuning exercise. So their average response time, the customer-facing transaction response time was 1.88 seconds. Just with GC tuning, without even doing any refactoring code or anything like that, we are able to drop that response time from 1.88 seconds to 0.95 seconds, which is 50% reduction, without any code change, without any refactoring. And it is minimal risk, right? And just changing the arguments, JVM arguments, I'm able to get. So how we are going to improve your garbage collection performance? See, you may watch this YouTube video talk, right? So in this talk, I've given examples or real out how you can go about optimizing the GC. See, optimizing GC is very, very common sense. It is not a rocket science. People make it appear like a rocket science. No, it's very common sense. So we can look into this one. So here I'm pointing out the best practices, the tools, and the right approaches to optimize the garbage collection performance. Okay. So friends, with this, I think I'm coming to the end of my talk, right? As the time is up, right? So I'm here. I'm open to take any questions or anything from you. Hello, Chris.
Great. Hi, Rob. Great. Thank you. Thank you. Yeah, so folks, now's the time to ask your questions. While they're typing in their questions, so when you look at all this, I mean, you really, it gives you a lot of information now. Can you predict a performance outage based on all this information now that you have?
Yes, that's a good question. Yes, see, in the talk, see, there are certain micrometrics. Using these micrometrics, you can predict an outage. So, Chris, I know we are on top of the hour, right? Do I have any time to show a slide or go through it, or what do you think?
Oh, you want to know about sharing something out now?
Yeah, or if time is out, then we can leave. I can pass this question.
If you can do it very quick, is this something you can?
Yes, just a couple of minutes. Yes.
Okay.
See, friends, one, you see, look at this. This is an garbage collection behavior of a very healthy application. I can see a full garbage collection running and the memory dropping all the way bottom. A full garbage collection running and memory dropping all the way bottom. It's a very healthy instance. But look at this garbage collection behavior. You see, when the garbage collection is running, the memory is not dropping all the way to this 200 MB mark. It just keeps on climbing slowly. This is telling already this application is having an acute memory leak. But look, this is where the graph gets very interesting, the garbage collection behavior. You see, when the full garbage collection is running, it's dropping, but after a point, it's not coming down. The garbage collection runs repeatedly again and again and again. So, friends, during all these good time, healthy time, if you study the garbage collection, the repeated garbage collection is not running. That's a micrometric. Studying the garbage collection behavior is a micrometric. What is garbage collection activity? If here the activity is very less, then it's a good sign that GC throughput will be like a 98, 99 percentage. But right when it enters into this danger zone, the GC throughput will die from 99% to 90, 85, 80. So GC throughput is one micrometric. If you study that, you can predict an outage very early. See, here it's the repeated GC starting happening at 8 a.m. But out of memory error happens only at 8:45 a.m. Several minutes, like 30, 40 minutes earlier, itself I can predict it. And I can tell you the outage. Yeah. Okay.
There is another question, but unfortunately, I'll let you answer him in chat. There's a question from Santosh Kumar, but you can respond to him in the chat there. We're gonna move on to the next phase here. So, Ram, I really appreciate you being part of LoadTestWorld here.
Okay. Yeah. Thank you. Thank you very much for giving me opportunity.
All right. Great. Bye now.